So, bit logic operations. We decided to classify bit logic operations into 5 categories. First, we have the basic logic operations. Basic logic operations only work with the PLC status word register. They do not require any additional memory and do not require help or use of the nesting stack inside the memory area of the PLC. This category entails basic AND operation and not or not, XOR and XOR not just means that it is reversed, the logic operation is reversed, and or what we call AND before OR operation, which is an instruction that is used to combine AND operations before an OR instruction. Second, we have nested logic operations. Nested logic operations require work with the status word register and need additional space in the nesting stack of the PLC. We will talk about the nesting stack when we reach nested logic operations. So this category entails AND with nesting opened, or with nesting opened. The same can be applied to AND not and or not with nesting opened, and the nesting closed operator. Then we will come to assignment operations. Assignment operations are mainly used to transfer the result of a logical operation or a logical combination into a desired address. First, we have the equal operation, then we have the set operation and the reset operation. We will talk about those later when we reach the talk about assignment operations. Then we will talk about flag control operations. They are not mainly used very often, but sometimes you need to use them. Basically, they are used to control certain bits in the status word register. Then we will talk about edging operations. And by edging, we mean the difference between a push button operation and a switch operation. A switch has two states, an on state and an off state. However, a push button has only one stable state. It is pushed for a little while from that stable state to another state and then back to the same state, which is why we use edging operations when we talk about push buttons. We will talk about these later when we get there. Now, before we proceed with the basic logic operations, we need to first recall some information about the binary flags of the PLC status word register. So, the PLC status word register is actually a 9-bit register. This 9-bit register can be divided into two parts. Each part has a few bits which we call flags. The first part, or the binary flags, these flags are basically used for logical operations. And the other part is called digital flags. These digital flags are mainly used with mathematical and compare instructions. So let's talk about the binary flags one by one. Basically, the first one, which occupies bit number 0 of the PLC status word register, is called the first check operation. this first check bit tells the instruction if it is the first instruction in a logic block or not. And the first check bit together with the OR status bit are both used to combine logical blocks. Secondly, we have the RLO, or the result of logic operation flag, in the first bit of the PLC status word register. So basically, after an instruction gets executed, the result of that instruction is stored back inside the RLO, or the result of logic operation flag. And the third flag we have, so basically we have the status flag. The status flag is actually a monitoring flag. It means that it's a flag only used for monitoring the program execution. So it is not useful to the program itself and does not affect the result of execution of a logical block. Instructions operating on an address display their status or display the value of that address inside the status word register, just for monitoring purposes, as we will see later. And then we have the OR status flag. The OR status flag is mainly used with the instruction we mentioned before, called the AND before OR instruction, in order to combine AND before OR logical operations. Then we will have the binary result. The binary result basically does not affect the result of execution of any logical block. It is only used in certain cases where we need to transfer the result of logic operation into it and then recall it back again after execution of some block. It becomes relevant when talking about jump instructions. And that does it for the PLC status word register. So we will be talking about how these bits change with execution of each of the basic logic instructions. So the first logical instruction we have is the basic AND operation. The basic AND operation is represented by the letter A, and you are required to provide an address in front of that instruction. This address can lie in any memory area that is addressable for the PLC. As an example for addressable memory areas, we have the inputs, the outputs, and the memory, the local data stack, and so on. We have different memory addressable memory areas of the PLC, but that's not our current topic. For our examples, we will be using addresses that lie in the memory area of the PLC. Now, before we talk about how the AND instruction affects the PLC status word register, we will first say that any instruction that has an address, or any logical instruction that has a binary address provided next to it, will always move the content of the binary address into the status bit, just for monitoring purposes, as we said before. And we will currently not talk about the binary result register. So our talk will be concerned with the first check bit, the RLO bit, and the OR bit. For the basic AND instruction, we have three cases. Each of them behaves differently from the other. But before we discuss these three cases, let us first look at our code and how it is organized. If we look at our example, let's say that we have three code blocks or three logical blocks. Each block has some logical instructions and some assignment instructions. These logic instructions must always end at an assignment instruction before you proceed to the next logical instructions. So basically, this logical instruction result must be first stored in some memory location before we move to the next logic instructions. So these can only come after an assignment instruction is used for the previous logic block. Assignment instructions, like for example the equal assignment instruction, will be discussed later in detail, but for now we need to know that an assignment instruction ends the current logical block, which is for example this block, and prepares the status word register for the next logic block, which is this block. So basically, before I can compute the result of this block, I basically need to end the previous block. And the way it actually does that is by changing 2 bits in the status word register back to 0. These 2 bits are the first check bit and the OR bit. So when the first instruction comes in a logical block, it must find these exact 2 bits to be 0. We can actually see that here if we run monitor mode. So basically, after this instruction, this bit, which is the first check bit, which is the first bit, and the fourth bit, which is the OR bit, are both set back to 0. The same works for this assignment instruction, and the same works for this third assignment instruction. Now, let's first focus at this logic block. This logic block starts with an AND operation. After that AND operation, there comes another assignment operation. And since this is only one instruction, we will see now that the value stored within that address will be moved to the RLO. What we're concerned with now, it was the assignment instruction does next. The assignment structure takes the value that is stored in the RLO and moves it to the address that is passed to the assignment instruction. So this will be useful as we look at the different cases of the basic AND instruction. So if we look at that example, we'll first look at the status bit. Let's look at M21.0. It is now set to 1. And as you can see here in the third bit, which is the status bit, you can see it is 1. After this is computed, the RLO actually becomes 1 because this is 1 and it is the first instruction, as we will say later. Now that the RLO is 1, the assignment structure comes, moves the value of the RLO to the address 21.7, which is actually stated here. So 1 is moved to 1, and also sets the FC bit and the OR bit back to 0. And now let's look at the different cases for the AND instruction before we proceed with our example. Our different cases are present when different values for the first check bit and the OR bit are present before the instruction is executed. So the first case we have is that the first check bit was 0 before the instruction is called, and the OR bit was 0, as we said before, which happens after an assignment instruction for the first instruction in a new logical blocks. So what will happen? Well, basically, we will just copy the value of the current address and move it to the RLO, and the first check bit will also be set to 1 in order to combine the result of the current logical instruction with the next logical instructions that come after it. So this is a start, but it does not necessarily have to be the end. And this is the first case we are talking about. So just let's go back to the code and look at our first case in our basic example. So here, or here actually, let's look here. And for our example, or for this example, let's suppose that the value stored in the first address is 1, the value stored in the second address is 0, and the value stored in the third address, which is 0.2, is 1. If we look at the status bit from here or from here, we will see that it just reflects the value that is stored in the address passed to the logical instruction. Now looking at the first AND operation, before it, we had this instruction set the first check bit and the OR bit to 0. So when this instruction came, it checked and found that FC was 0 and the OR bit was 0. So it deduced that it is the first instruction in a logical block, and therefore the value that is stored in that address, which is actually 1, here is actually moved to the RLO. So 1 is moved to the RLO. And this is how the status word register looks after execution of this first instruction. Now let's move to our second case. In our second case, let's say that the first check bit was already 1. So this instruction can't be the first instruction, and the OR bit was 0. In that case, what we will do is that the value of the RLO now needs to be set to the AND operation of the value stored in the address and the previous value of the RLO bit. So let's actually look back at it. If we look at it, if we look at the second instruction, before the second instruction, it will check, it will see that the first check bit is 1. And as the first check bit is 1 and the OR bit is 0, what the instruction will do is that it will take the current value, which appears here in the status, which is 0, and does an AND operation with the previous value of the RLO, which is 1. 0 and 1 is, of course, 0, so 0 is stored as a new value of the RLO after execution of the second instruction. And this is the second case for the AND instruction. As for the third case, this third case is when the first check bit is 1 and the OR bit is 1. This state only appears when we talk about the third instruction, which is the AND before OR instruction. So we will talk about it later. So for now, let's move back to our example and see how it works. So the first instruction, as we said, comes, checks, sees that the first check bit was 0 and the OR bit was 0, deduces that it has to move the current value of the RLO, the current value stored in the address to the RLO, and therefore the RLO after this instruction becomes 1. Now the second instruction is called, it sees that the first check bit was 1 and the OR bit was 0, and therefore it will keep the first check bit as 1. It needs to combine the value stored in that address, which is here in this status bit, which is 0. It will need to combine it with 1, and 0 combined with 1 with an AND operation results in 0. Now we come at the third instruction. The value stored in that address is actually 1. This value is reflected by the status bit in the status word register. It checks previously and sees that the first check bit was 1 and the OR bit was 0, and therefore it needs to combine the current value with the previous value of the RLO, which means that 1 is combined with 0 and yielding 0. Then the assignment structure comes to end that block, and this assignment structure will first set these two bits back to 0, which are the first check bit and the OR bit. They will be set back to 0 and moves and does not change the value of the RLO, so the RLO remains the same, and moves the value of the RLO to the address, which is M0.7. This value is 0, so the value that will appear in that address will also be 0. And therefore we have ended that logical block. And of course, the assignment operator itself reflects, or the status bit that is facing after the execution of this assignment operation will always reflect the new value that is stored in the memory address that comes after the assignment instruction, which is 0. So basically, if we change M0.1 to 1, what we expect is that the result will be 1, and as we can see here, it actually, M0.7 actually becomes 1. As you can see here also from the status bit, it also becomes 1. All of these became 1s as we previously discussed. The assignment structure always sets the first bit and the fourth bit, which are the first check and the OR bit, back to 0. And now we are done with explaining the basic AND instruction, except for the case when the first check bit is 1 and the OR bit was previously 1. We didn't also talk about the case when the first check bit is 0 and the OR bit was 1. This case actually never happens. As we will see later, no set of instructions can yield this result. So this is actually not important because it never happens. Now that we have finished talking about the basic AND operation, we will need to next talk about the basic OR operation and then the AND before OR operation before moving to the next category of bit logic operations. But that will have to be discussed in the next video. So thank you for listening. Please like and sub to the channel.